Hello everyone. Today we are going to talk about Motion LM, multi-agent motion forecasting as language modeling. The motivation behind this research is to enhance interactive motion forecasting. The current methods in use have limitations in capturing the joint distribution over multimodal futures effectively. This is a significant challenge as it hinders the accurate prediction of future movements. Existing approaches also face difficulties in latency-critical settings. This is a crucial aspect to consider, especially in real-time applications where quick responses are necessary. The inability to leverage large datasets of scene rollouts effectively is another shortcoming of the current methods. Large datasets provide a wealth of information that can be used to improve the accuracy of predictions. Moreover, existing methods struggle to form a search tree over the multi-agent action rollouts. This is a crucial step in the process as it allows for a more comprehensive analysis of possible future movements. The approach detailed in this paper aims to overcome these limitations. It introduces a method that leverages multi-agent rollouts over discrete motion tokens. This approach is designed to capture the joint distribution over multimodal futures more effectively, thus improving the accuracy of interactive motion forecasting. In summary, while existing methods have made significant strides in interactive motion forecasting, they still face several challenges. This research aims to address these issues and push the boundaries of what is currently possible in this field. The authors of this paper are addressing the challenge of interactive motion forecasting. This problem is significant due to its potential applications in areas such as autonomous driving and robotics, where accurate prediction of future movements is crucial for safe and efficient operation. Previously, existing methods struggled to effectively capture the joint distribution over multimodal futures. This limitation could lead to less accurate predictions, particularly in complex environments with multiple interacting agents. Furthermore, these methods might not be well suited for latency-critical settings, where quick response times are essential. They also might not be able to fully leverage large datasets of scene rollouts or form a search tree over the multi-agent action rollouts, which could limit their performance and scalability. To address these issues, the authors introduced a new method that leverages multi-agent rollouts over discrete motion tokens. This approach allows for a more comprehensive representation of the multimodal future distribution, which can lead to more accurate predictions. The authors also proposed using the trained model in model-based planning frameworks, which could further enhance its utility. Moreover, the authors explored the use of distillation strategies from large autoregressive teachers. This could enable faster student models to be deployed in latency-critical settings, addressing one of the key limitations of previous methods. The authors' approach led to a significant improvement in performance, establishing a new state-of-the-art on the WOMD Interactive Prediction Challenge. This demonstrates the effectiveness of their method and its potential to advance the field of interactive motion forecasting. Section 1. Problem formulation and approach. The authors of this paper aim to enhance interactive motion forecasting by capturing the joint distribution over multimodal futures. They achieve this by leveraging multi-agent rollouts over discrete motion tokens. This approach is a departure from previous methods that may not effectively handle latency-critical settings or utilize large datasets of scene rollouts. The author's unique formulation of the problem allows for a more comprehensive and efficient prediction of interactive motion. Section 2. Methodology and experiment design. The authors introduce a novel method that uses rollouts to represent the multimodal future distribution. They generate a sufficient number of samples from the model, which are then clustered down to k=6 modes for evaluation. The model is trained using the WOMD Interactive Prediction Challenge dataset, a robust and comprehensive dataset that allows for a thorough evaluation of the model's performance. The authors also conduct ablation studies to evaluate the performance across varying interactive attention frequencies and numbers of rollouts, ensuring a comprehensive understanding of the model's capabilities. Section 3. Improvements and innovations. The proposed model establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge, surpassing the previous top entry on Joint Map with just 32 rollouts. This demonstrates the effectiveness of using rollouts for interactive motion forecasting. The authors also propose future applications of the model in model-based planning frameworks and in exploring distillation strategies from large autoregressive teachers. This shows the potential potential of the model to be deployed in latency-critical settings, marking a significant improvement over previous methods. Technical results: 1. The proposed model has achieved new state-of-the-art performance on the WOMD Interactive Prediction Challenge, surpassing the previous top entry on joint map with just 32 rollouts. 2. For the final leaderboard results, the model used 512 rollouts per replica. 3. The model with 27 M parameters was found to overfit, while the model with 300K parameters underfit. However, both the 1M and 9M models performed decently, indicating a balance between model complexity and performance. Key insights and implications: 1. The results demonstrate the effectiveness of using rollouts for interactive motion forecasting. This suggests that the proposed method can handle complex multimodal future scenarios more effectively than previous methods. 2. The proposed model can be used in model-based planning frameworks, indicating its potential applicability in real-world scenarios. 3. The model can be used to explore distillation strategies from large autoregressive teachers, suggesting potential for further optimization and efficiency. 4. The model can be deployed in latency-critical settings, highlighting its practical utility in time-sensitive applications. Ablation studies and implications: 1. The performance of the model was evaluated across varying interactive attention frequencies and numbers of rollouts. This helped in understanding the impact of these parameters on the model's performance. 2. The study found that the model's performance improves as additional rollouts are utilized, indicating the importance of generating a sufficient number of samples from the model. 3. The study also found that the model with 9M parameters is used for the main results, suggesting that this model size offers a good balance between performance and complexity. Key highlights of the paper: 1. Key insights. The paper underscores the effectiveness of using rollouts for interactive motion forecasting. It suggests that the proposed model can be utilized in model-based planning frameworks and can be deployed in latency-critical settings. It also highlights the potential of the model to explore distillation strategies from large autoregressive teachers. 2. Key contribution. The paper introduces a novel method for interactive motion forecasting that leverages multi-agent rollouts over discrete motion tokens. This approach effectively captures the joint distribution over multimodal futures, a task that existing methods may struggle with. 3. Key idea. The core idea of the paper is to generate a sufficient number of samples from the model, representing the multimodal future distribution. These rollouts are then clustered down to a specific number of modes for evaluation. The model is trained using the WOMD Interactive Prediction Challenge dataset. 4. Key results. The proposed model establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge, surpassing the previous top entry on joint map with just 32 rollouts. For the final leaderboard results, 512 rollouts per replica are used. The model with 9M parameters is used for the main results, demonstrating that the model's performance improves as additional rollouts are utilized. 5. Key conclusion. The paper concludes that the proposed model has significantly improved the state-of-the-art in interactive motion forecasting. Future work will focus on leveraging the trained model in model-based planning frameworks and exploring distillation strategies from large autoregressive teachers.